Hello, my name is Charlie Cai. Today I'm going to introduce SPI over LVDS implementation for test and measurement applications. LVDS devices offer high noise immunity, minimal EMI, low jitter and skew. They are low cost, low power, and can be used to transmit both data and clock signals. SPI over LVDS can be implemented as single board application or board-to-board application. Here's a block diagram showing the two implementations using SN65 LVDS31 and 33 LVDS driver and receiver. SN65 LVDS31-33 offers high noise immunity, low EMI emission, and a wide -4 volts to 5 volts common mode input tolerance. The ADC output waveform was produced with 30 MHz SPI clock over 50 cm ribbon cable under noise injection. In this example, sending SPI signals over LVDS interface provides significant noise reduction compared to without LVDS. With TI's broad LVDS portfolio, many configuration options are available. Here we present two options for standard 4-wire SPI bus. Option 1 uses one pair of quad-channel LVDS driver and receiver, DS90LV047A, 48A, and one pair of single-channel driver and receiver, DS90LV011A, 12A. Option 2 uses 4 pairs of single-channel LVDS driver and receiver, DS90LV011A, 12A. Both options offer low TX-RX propagation delay. Option 1 has lower bump count but takes slightly larger PCB area compared to Option 2. Here's a solution size example showing the needed PCB space for 4-wire SPI implementation. Option 1 roughly needs 171 mm², and Option 2 roughly needs 140 mm² additional PCB space. Both solution sizes are small, but Option 2 saves slightly more PCB space. In this example, we are showing a 5-wire SPI implementation, including a data-ready signal. Option 1 uses a pair of quad-channel driver and receiver, DS90LV047A, 48A, and a dual-channel driver and receiver, DS90LV027A, 28A. Option 2 uses two pairs of SN65 LVDS31 and 33 quad-channel LVDS driver and receiver. Compared to Option 2, Option 1 offers lowest propagation delay, which allows faster SPI data rate or longer trace or cable, but does not have the wider common mode input range that Option 2 offers. The SPI over LVDS solution is not limited to what we have shown here. TI offers 1, 2, 4, 8, and plus channel LVDS driver and receivers that's suitable for different applications. In SPI protocol, data output from master is typically sampled on the rising edge of the clock, and the data returned from the slave is typically expected to reach the master on falling edge of the same clock period. Delays introduced in the signal chain may cause mismatch between data and clock. In this case, it is important to consider the worst-case SPI speed and the cable or trace length. The equation to calculate worst-case SPI speed or cable length is shown here. It is possible to route the S-clock signal back to the SPI master and configure the master to sample returned data with the returned clock. By implementing SPI bus this way, ideally the propagation delay is eliminated. The worst-case calculation is simplified as this equation. We also have a TI design, TIDA060017, that showcases transmitting SPI signal over LVDS interface. This design uses SN65 LVDS31 and 33 as the LVDS driver and receiver. A ADC ADS89110B is chosen as the SPI slave. For this TI design, a few tests was performed and have shown that SPI over LVDS interface offers high noise margin, at least 3 meter communication range, and -4 volts to 5 volts common mode input range compared to single-ended SPI application. For more information, please visit ti.com/lvds.